Okay, today we're going to take a closer examination using some information we've already learned, a formula, force equals mass times acceleration. We're going to focus, instead of just on calculations like we did in our last unit, we're going to take a closer examination and attempt to elucidate the relationships that exist within that equation. Right? Oftentimes, this is known as Newton's second law. More official name would be the law of force and acceleration. And instead of just solving, what we want to do is find out what is the relationship between force and acceleration and between mass and acceleration. As we'll see in a moment, that relationship is going to be different. So on your screen, you see a few things. There's a track, there's a motion detector, and you should see in the background a position versus time graph. With that, we are going to look at the slope, hopefully curved, if it's accelerating the way it should, the curved slope and how that slope changes. They're going to be positive because it's going to move away from our motion detector, which will serve as zero position. But will that slope be increasing, getting steeper, or will it be decreasing, getting more shallow? That's what we're going to see today. So in two experiments, in the first experiment, we're going to hold mass constant. The car itself is a quarter of a kilogram. The mass we're going to put in the car is going to also be 250 grams for a total of half a kilo. All right? What we're going to do here, as that's constant, is we're going to manipulate the amount of force we put onto or have applied to the car itself. So in doing so, we're going to start with just 25 grams converted out. It's going to be a little bit of force, right? And we'll find out what that is here. So let's take an initial reading and see what this force will do to this mass. So as you can see, it starts a little bit away from a zero position. Here's where I stopped it at the end, so it leveled off. In between, for every unit of time, it's covering more run. All right, for every run, there's more rise, is what I meant to say. I'm sorry. So as time increases, the position increases even greater. So this object is accelerating. What we're going to do now is we're going to double that force. So instead of 25 grams on the bottom here, we're actually going to put 50. So if we double the force, think, before I do this, what do you expect to see happen to the acceleration? Mass is held constant. As we double the force, we would expect what to happen to the acceleration? So just looking at the car qualitatively, you would have seen that it looks like it's going faster. The rate of velocity change has increased, and our graph backs that up. If you notice, we covered less time overall, but the same distance. So if we cover more or the same distance in least or less time, then that's going to end up being a greater rate of acceleration. So what we're going to do now is we're going to double it again. So this is going to be 4 times greater than our initial trial, but twice as much as our second trial. So we started with 25, went to 50. Now there's going to be 100 grams of force acting on this object. So again, think, what's going to happen? As we increased force last time, acceleration increased. We've increased force again by another factor of 2 or factor of 4 over our original trial. What's going to happen? Now we could really see some results. Look how steep this slope is. Again, we started a little bit away from zero position. This is before I released the car, after I started collecting data. This is when I stopped it. In between, you can notice that we're nowhere near the 2-second mark. It takes nowhere near that much time, maybe a little over a half second to cover this distance. Distance being about, 75 or so centimeters. So it takes nowhere near same amount of time as it did initially, indicating that acceleration is increasing. So the relationship, we give this relationship a name, it's directly proportional. The relationship between force and acceleration is one that changes in the same direction at the same rate. It's directly proportional. If we doubled the force, we actually doubled the acceleration. In this last trial, we quadrupled the force. We actually saw the acceleration go up by a factor of 4 as well. If we were to cut the force in half, then the acceleration would get cut in half. So the relationship between force and acceleration is one that is directly proportional. So now we're going to hold force constant. We're going to leave 50 grams on the force hook out here. And we've already seen what happens with one mass on here. Let's put a second. So now our total amount that we're going to start with is going to be 0.75 kilograms. 0.75 kilograms. That's the car itself and 2 masses. There'll be our initial reading. So you can see already just from when we did this a little bit ago, because we also did it with 50 grams. But with two masses instead of one, the slope is a little more shallow. You can see it takes almost 2 seconds exactly to cover the same distance. So acceleration's already gone down as we've added mass. That's a little bit different than what we saw in our initial test. So let's add some more. We're actually going to double this. We're going to go from 0.75 up to 1.5 kilograms total. So if you double the mass, think, what do we expect to happen to the acceleration? So you should see that the car itself is moving slower. As mass increases, the acceleration went down. Look how much more time it took to cover that same distance. We're well beyond our 2-second mark now. So now we're going to go from doubling it again to now we're going to add another factor. It's going to be 3 times greater than it was initially. Now the total, and another 0.75 kilograms here. So our total mass now is 2.25. Qualitatively, you should have seen that, yes, it's going a lot slower as I've added mass. Graphically, it backs that up. Look how shallow our slope is. The unit of run versus rise is nowhere near what it was initially. So again, with force and acceleration, we see a directly proportional relationship. As force increases, acceleration follows suit. As force decreases, acceleration decreases in the same direction, right? It's both decreasing, but by the same factor as well. On the other hand, mass and acceleration have an inversely proportional relationship. As one quantity goes up, the other goes down. When we doubled the mass, acceleration was cut in half. We tripled the mass, acceleration was cut down to 1/3 of its original. If we were to cut the mass in half, acceleration would then double. So there's direct and inverse relationships. These are a topic that's introduced today, but we're going to be talking about this for the remainder of the year.